Okay, so good evening. Now we can start with the PT student now to mark attendance. Is anything, if nothing, you off your mic. Hello. Yeah. Okay, so we see next. Yeah. Okay, now for PT 20 to mark attendance. Okay, one more. Okay, now for ODL student. Yeah. Okay. So, okay, so we, okay, so far no objection from students. Therefore, we consider fixed up means the weekday class we start at 7:30, end at 9:30. Okay, starting today. Okay. So, so as usual, anyone who came a bit late, let me know. I can mark your attendance. Yeah. So for the previous class, we already finished the multiple linear regression and started the vector analysis. Okay, so vector analysis we discussed. We actually want to do data reduction, yeah, for many variables, yeah, reduce to few variables. Okay, but for the we see got two. One is a vector analysis, okay, which is common vector analysis. Okay, so where we find the common variance, yeah, among the vectors. And the other one is the principal component analysis, where we actually want to um, want to find the important, do the ranking. It means some important, some variable are important. Okay, consider the first factor, second, and so on and so forth. Okay, so of course for each factor also come from few variables, yeah, like that. Okay. Okay. So that's what we discussed in the previous class. And one more thing we also discussed, we can find the correlation easily from the SPSS. Okay. And then after this, we can actually also do the uh, regrouping. Okay, regrouping so that we can easily find the vectors. Okay, find the vectors. Okay, so we call this rotation. So you will see rotation. either today or tomorrow. Okay, so that's what we discussed in the yesterday class. Yeah. Okay. One more thing, cut-off point can be 0.6 or 0.7. Normally these two. Okay. So use either one is not wrong. Actually, yeah, not wrong. Okay. But you must mention in your but you must mention you either use 0.6 or 0.7. Yeah. So okay. Any question you want to ask? Yeah. Okay. So if no, now we continue with our discussion. Okay, no one. Okay. So we see we already discussed the two correlation table. We call this correlation matrix. Okay. So okay. So means once we done the rotation, yeah, you will get this. Yeah. I mean you'll get a different table, but will be easy for us, yeah, to find the factor. Okay. Okay, we should do this yeah, maybe later. Okay, see how, yeah. So yeah. So we see some application. Okay, today I continue. Today 7 September. Okay. So now we see some application of the factor analysis to a fast food restaurant. Okay. So let's say here based on the sorry. Okay. So based on the output, we can make it two factors. Yeah. Okay. One and also two. From the variables, we can get two factors. Okay. So and then we need to find the name. This based on these three factors, we know they are in the same group, same factor. Please you give a name to represent these three variables. So here also got three variables. Yeah, and then we want to group it, find a name. A general name that can be used to represent these three variables. Okay, so I think you have the answer already. First one is the food quality. Okay, so second is maybe service. Yeah, okay, yeah, service quality. Okay, therefore got two factors. Okay, so means well, but I think for this one, I still not easy to do the grouping. Okay, to find a name, yeah, a name, a factor name to represent each factor. I think not too easy for this part. Okay. Okay. So if no question, now we see.
So,
yeah.
Can I ask, I mean, if we are not able to come out a meaningful name, can we put a dummy to represent the grouping? Like, for example, group 1, group 2, group 3, can we name in that?
No, not that. Okay, good question. Okay, actually, okay. So in practice, we got two methods to find a name. Yeah. Okay, two methods. So means what? Means like this is still very easy. Okay, but let's say in practice, if you not easy to find a name, actually you can have two methods. So first method, you find the even let's say here got four. Yeah, four variables. You cannot find a common name to represent all the variables. You can find another name that can be used to represent three. At least three variables. Also consider good. Okay, like this. So example here, return policy looks like not relevant compared to other three. Can you see? Okay. So means maybe it's overall experience, right? Maybe it's overall experience in the store. Can you see? Return policy is also experience in-store service, store atmosphere. Yeah, therefore it's more to like overall experience or shopping experience like that. Okay, so like that. Okay, means if you cannot find a factor name that represents all the variables, at least it can be used to represent most of the variables. Also consider okay. Okay. This is the first method. Okay. So second method, let's say here got two. Yeah, we see the bottom one, got two, price, level, and product quality. Yeah. So any suggestion? And let's say you cannot find a name to represent these two variables. Therefore, you can just find you just use the name, you just use the variable that is more important than others. Okay.
So just call it product quality.
Yeah, something like that. Okay. Something like that. Okay. Of course, we have another method to determine which variable is more important. Yeah. Later you will see. Yeah. Okay. 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 So now continue.
Sir, one
Yeah.
question on this V1. In this case, only V1. There's no other correlations with, you know, they're only comparing to itself only.
No,
So
not
why
like
do
that.
we? Oh, okay.
Not like that. V1 actually have can you see this value 0.765. Okay, therefore V1 has the positive and strong relationship with V5, 1 and 5. Okay, okay. Don't worry, I'll show you something that you may ignore, you may forget. So actually, if you want, you can put here 0.765. Okay, no? Understand? Therefore, 0.765 is the correlation between 5 and also 1. You can see? And because we already have one value here, 0.765, therefore we did not repeat again here. Okay? It's remember the triangle. Okay? Yeah. You needed here 6.3. Example 6.3 is here 6.3. So here actually is also 0.423. Same value. But we did not show it. Okay? Yeah.
We call mirror, right? Mirroring.
Yeah, correct. Correct. You are right. It's mirror. Okay, this one is a mirror. You can say that it's correct. It's correct. Okay, it's correct. Okay. So we done already for this part. Now we see next. Yeah. So this is a factor analysis decision process. Okay, you must determine the objective. Okay. So basically, it's more to E, F, A. Yeah, exploratory factor analysis. Okay, discussed a bit in the previous classes. Okay. So we just explore compared to the SEM where they actually use the C, yeah, confirmatory factor analysis. Yeah. So therefore, CFA can be used to test hypothesis, but now this one cannot. There's a main difference, okay, between these two. Okay. So we just do the grouping, but not involved in the testing of hypothesis. Okay. Design a factor analysis needs more to discuss the sample size and so on and so forth. Okay. The assumption, of course, must be metric. Yeah. Soft reminder. Okay. Your data must be all metrics, including your independent and dependent. Because your question number 1 involve dependent, independent. Number 2 don't have. But you still must handle you must also fulfill the requirement for the question number 1, okay, which is the multiple linear regression. Okay, so all must be metric, and you must let me know which one is the dependent, which are the independent variables. Like that. Okay. Okay. So and then we do testing, and then interpreting the factor. Okay. Means you have how many factors? You have 4 or 3. Yeah, and then factor 4, factor 1 actually consists of which variable? Yeah, example here, question number factor 1 means 3, 8, 9, 2. Okay, V3 until V2, you have 4 variables. Okay, for maybe these 4 group together to form factor 1. 6, 7, 4 group together to form factor 2. 1 and 5 group together to form factor 3. like that. Okay. Okay, so if no question, sure, yeah. Okay, so if no, now we see next, yeah. Okay, so now we are, we are here. Okay, so we also discussed a little bit in the short while validation of the factor analysis. Okay, and also the additional use of the factor analysis result. Okay, we do this now. So therefore, this one in this chapter we only see the exploratory, the FA. FA means factor analysis. Okay, so CFA will be for the SEM discussed later in the end of the chapter. Okay, the final chapter. Okay, so now you see we specify the factor analysis. Yeah, okay. So means you actually want to focus on either, but this one not too important. It's okay. Just discuss a bit the R analysis or Q analysis. So R is the Q is for the respondent. Okay. So R actually is for the variable. Okay. To analyze the variable or the respondent. So okay. So for this one actually for the respondent, it will be the cluster analysis. But for us, still more to the variable. Okay, you focus on the variable, not the respondent. Yeah, we call this R analysis. Okay, so this one will be next chapter. Yeah, got it. After this chapter. Okay. Okay. So we want to do data summarization or data reduction. Yeah. So for factor analysis, it's more to summarization. Okay. Deduction will be PCA. Okay. But when we discuss factor analysis, not easy to run away from the PCA because these two are very similar. Yeah. Only a bit different. Okay. But here the data summarization is factor analysis. Okay. Data reduction is PCA. Okay. So here, but some key terms still can be used here to differentiate these two. Okay. So factor analysis, we find the common variance. Okay, we find the common variance. But PCA, we do data reduction. Okay. Means let's say got first four variables, yeah, you group together, become factor 1. The method that they do calculation actually is to find the common variance. Means these four, they are quite similar. You can think it's like they are R squared. It's similar if R squared, yeah, the common variance are quite high among these four variables. Then it's grouped together to form a factor. Okay, yeah. Okay, so now we see we also can use the factor analysis with other techniques. Means the outcome or the result that we get from factor analysis may be used in other technique. Example, like the multiple linear regression. Okay, so because in the multiple linear regression, yeah, not too flexible. Means they only want one variable. Yeah, to repeat. I mean one column of the data to represent one variable. But here you got, let's say you got four. You got four variables. You cannot put in everything because they only want one, but you got four. Yeah. Example, they want okay, food quality. You use example just now, food quality. But now you got four. You got four variables. Which one you want to use? Okay. Therefore, we can use this filter analysis. They finally come up with only one column of the data. They copy to the filter to the multiple linear regression. Okay. Therefore, you can use the filter analysis with other techniques. Okay. This is the first stage 1. Okay. Any question? Yes. Stage 1.
Sir, just want to ask on this because for this slide that you showing just now, you're saying that the grouping is based on the the common variate, which is similar to R square.
The idea is similar with R square. Similar.
Yeah, it's similar to R square. But in the previous slide, you are using a correlation, which is the small letter R. So which is correct? Just wondering.
Okay. Okay. Good question. Yeah. Actually both correct. Yeah. Both correct. Yeah. So if you're saying the common variance, actually it's also talking about the correlation between the 4 variables. These 4 they correlate to each other. They're highly correlated like that. Okay. Yeah. Yeah. Same thing. Yeah. Same thing. Okay.
So what is the best practice? Are we normally use R square as a starting point or the correlation as a starting point?
Do use this. Yeah. Do use this. Yeah. Use R. R is better. Correlation.
Okay. Okay. Got it.
Okay. You? Okay. So you see this now. Okay. Data summarization derive underlying dimension that were interpreted and understood describe the data in a much smaller number of concepts than the original individual variable. Okay. So we summarize it. Okay. That's why we use vector analysis because we make it become lesser variables. Okay. So we under the data reduction, we extend the process of data summarization. Yeah. So by deriving an empirical value, we call it vector score or segmented scale. Yeah. Means we can find it, we can do this when you see the output. Okay. So that's what I mentioned just now. We can use the output and then apply in the multiple linear regression. Okay. So by using these two, can be vector score, can be also the segmented scale. Okay. Yeah. Okay. Already discussed. Okay. And then for each dimension, and then we substitute this value here for the original value, and then use it in the multiple linear regression. Okay. So this is more to what we are doing now. This is more to PCA, but actually we can also do both in the vector analysis. Okay. That's why I say PCA and vector analysis actually quite similar also. They're different, not too much. Okay. So we see. If no problem, now we see next. Yeah. Means you can get this from the output, the vector score and also the segmented scale. So you see, you got two types of vector analysis: EFA and also CFA. EFA is used to discover the vector structure of a construct and examine its reliability. Okay. So, as I mentioned, you will see this is a vector structure. You got 20 variables. You make it become only 4. Okay, vector 1, vector 2, vector 3, vector 4. Yeah, it's more structured compared to we just mentioned the 20 variables. Okay. And then we can also see the reliability, which is using one of them actually is using the correlation. Okay. So of course, the term that we are going to use is not the correlation, but it's loading. Okay, it's okay. Introduce one or two new terms. Loading is the correlation between the vector and each construct. Construct can be also the variable. Don't worry too much. Construct is also like this. Yeah, all this, if you use construct, also not wrong, actually. Okay, in our context. Okay. Okay. So, of course, in general, the higher correlation, because it's loading actually. Loading, again, loading is the correlation between the construct and also the vector. Okay. Okay. it's data driven. Means we didn't control the output. Actually, if you want, you can also put in 4 or 5 factors. Yeah, in the when you do the testing. Okay. Okay. So CFA, you can actually based on theory, and then you say that this data I suppose have 4 factors. Yeah, based on theory. Means you have to control. You have to control on the outcome. You want 4 factors. So you just want to confirm whether the data they match or not, consistent or not with the theory. Okay, therefore you can do testing of hypothesis under the CFA. But this one will be later. Okay, under the SEM. Okay. Okay. If no question, now we see. Yeah. Of course, minimum must be 2, but sometimes output give us only 1. If you have 2 lesser variables, okay. Okay. Of course, in practice normally more. Yeah, cannot be only 1 or 2. There should be more. Yeah, means you should have more variables, and then you may have 4 or 5 factors. Okay, next. Yeah. So designing factor analysis. Yeah, I think before I forget, you can stand by first using the SPSS. Yeah, so we suppose. Yeah, in a short while we're going to use it. Yeah, today confirm we are going to use SPSS. Okay, you stand by with your SPSS. Okay. Yeah. Okay. So if no question, now we see 3 basic decision calculating of the input data. Yeah, R or Q. You normally use Q. You Q for the factor analysis. Your R is for the CA, your cluster analysis. Okay. So this one also important. You see this in the next slide. That means what means determine the number of variables. Okay. Here also good to answer the question asked by a student just now. Okay. So the measurement property, of course, is metric. Okay. And also the sample size. Okay. So in general, okay, more is better. Okay, sample size. Okay. So of course, we have a rule to follow. Okay, here. Okay. Filter analysis is performed most often using metric variables. Okay, consistent with your assignment. So sometimes can use dummy, but it's already different, a bit more advanced. Yeah. So just like the multiple linear regression is normal, everything metric easy, but dummy a little bit more advanced, a bit. Okay. So a small number of dummy variables can be included in the set of metric variables that are factor analyzed. So, but here we are not going to touch the dummy variable, only the basic. Okay, for the factor analysis. Okay. If the study is being designed to review factor structure, so you try to have at least 5 variables for each proposed factor. Means let's say your target is 3 factor. Means you should have 15 factors altogether. 3 times 5, you get 15. Okay, this is some guideline. Okay, this is more to the research design. Okay, so the actually is sample size. Okay, sample size. Yeah. Okay. Okay, it's okay. The sample is okay. Yeah, because this the term observation, meaning that the sample must have more observation than the variables. This is n. This is the total variables. Remember, factor analysis is one kind of interdependent analysis. Therefore, no independent or dependent, or same variables. Okay. the minimum isolated sample size should be 50 or above. Okay, minimum 50. So you see, as I mentioned just now, n more. Yeah, more sample size is better in statistics. Okay. So maximize the number of observation for each variable. The minimum is 5, and then at least 10. 10 is better. Means minimum is 5, but 10 is better. Yeah, for each variable. Okay. So repeated lah. Okay, repeated.
Sir, for previous slide, I just want to understand a little bit on this minimum. You're talking about at least 5 variables for each proposed factor. So in our assignment, because we are talking about, if I'm not mistaken, 8 variables, right? So are we saying that we will be only talking about probably one factor, like 1 point something? Less
No, you
than
see, 8 metric, 8 times. Which one are you talking?
The second bullet point, there's 5 variables for each proposed factor. So are we saying that we are talking about less than 2 factors for our assignment, because we are talking about 8 variables?
Yeah, maybe you get only 2 or 3. Yeah, 2 or 3. Yeah, but the problem is that if we put more strict requirement, maybe not easy for you to get the data. Okay. Of course, that's why I say more is better. If you can, you may find maybe 20 variables and then 1,000 observation, if possible. But that's the minimum requirement stated in the assignment. Okay, minimum. Okay, yeah. So you can think also this way. This one can be the requirement for your capstone. It's more strict, yeah, more strictened compared to the assignment. Yeah, like that. Okay, if no problem, now we see next up. Okay, we have any other question from the online student? Okay, no. So, okay, so continue. Yeah. Chantana. Yeah. Okay. So for this one, we are going to start with the SPSS. Okay. So it says using the MSA. MSA means measure of the sampling adequacy. Yeah, means your sample good or not good. Right. Yeah. Some students already get the what they call the data. You can start to do analysis if you want. Use your own data. But for me, I'm still using the data that already uploaded to the what they call to the model. Okay. Up to you which one you want to use. But for me, I just use the same data set. Okay. Okay. So we see MSA. Yeah. So MSA is measured by KMO statistics. Yeah. So this statistics is developed by these 3 persons. Yeah, KMO. Okay. But the purpose is to measure the sampling adequacy. Is sample good or not good? Yeah, for us to run data analysis. To run the factor analysis. So the KMO predict if the data are likely to factor well based on the correlation, yeah, and the partial correlation. Okay. Okay. So therefore, in general, the correlation should be high. Okay, should be high. KMO can be used to identify which variable to drop from the factor analysis. Let's say you have, okay, therefore, but 8 is still considered okay. Yeah. Okay. So let's say you have 8 variables, 8 metric variable already good to proceed. Okay. But let's say you have 25, yeah, 25 variables in your data set. Yeah, after KMO, maybe only one or two. Maybe one or two should drop. Maybe. Yeah. You will see the criteria in a short while. Okay. So because lack of the multi-collinearity. Okay. Yeah. So this one is one of the advantage, yeah, of the multi-collinearity. Okay. So therefore, a little bit multi-collinearity is still okay. It's still good. Okay. Okay.
Pastor, if they decide to drop either, I mean, one or two variables, so the dropout variables, they are like, is his own factor or is totally just taken out from the
Totally taken out. Totally taken out. But okay. Actually, don't worry too much. I show you now. Yeah. So okay. Okay. So let's say you 1 plus 8 correct not? Based on the assignment. Hello, anyone can confirm? I cannot remember. I think should be correct.
Yeah,
1 plus. Okay. So means one
dependent.
Yeah, got it. Okay, yeah, thank you. Yeah. So one metric, but metric cannot be two. Independent can be more. Okay. So now 1 plus 8. Okay. Let's say your I know some of you want to ask this. Okay. Let's say like this. Your one dependent and then one 9 independent. You've done already. Number one example. Okay. And then now you use this 9. You put this 9 together. Yeah. Correct not? Okay. I think 9 all can be used, yeah, to do the factor analysis. Yeah. Okay. Yeah. Okay. Okay, you see here? Okay. It's okay. We follow this one. We follow this. Yeah. So that means you only use the metric independent variable. Yeah. So only use the metric independent variables. So therefore, now you use 8 independent variable. Yeah. Same data set. You do the factor analysis. Okay. But let's say one of them you must drop. You drop one. Okay, you drop one, you got only 7 for you to do the factor analysis. Therefore, you show me, I mean, you show it in the assignment that you drop one because of they cannot meet the criteria of the MSA. Because the KMO statistics are not good. You will see the criteria in the show one. This means you still can keep your answer of Q1 and then you proceed use for the Q2 with only 7 variables. Still okay. Don't worry. Okay. Yeah. In general, if you let's say finally you drop 2 variables in this stage, still okay. Don't worry. Okay? But you must show the output so that I know why you drop the variables. Okay.
So just to clarify, just now, the other point is mentioned is on the at least better is 5 variables for one factor. But I thought just from what you taught yesterday, when we do the rotation, by right the SPSS they'll group them into the triangle as per their factor. So that means the number of factors is depending on what the rotation have done, right? I mean, we cannot decide one, right?
Is correct. Okay, this is the guideline. Okay, this okay, wait. I think okay, are you saying this one? The point number 2. At least 5 variables for each proposed factor.
Yeah. Yes.
Okay. Okay. This is a guideline. Yeah. But the final outcome we cannot change. Can I say? Means you believe the result should be significant. But if finally not significant, you cannot change anything. Can I say like that? Okay. So what you believe and the final outcome can be different. Right? You have no control over the data value. You only can know the theory from theory. Suppose like this. And this is a guideline. They said it at least 5. So means let's say finally maybe only get 3 variables, but still good. You got 3 variables to form a vector. Why not?
Okay.
Okay, yeah, it's like that.
Sorry, sir.
Yeah.
Sorry, sir. For the multi-collinearity, last time we learned this in the linear regression, multilinear regression, and it's not considered a good thing. But in factor analysis, multi-collinearity, can I say is a good thing to check whether there's a correlation?
Yeah. You're right. You're right. Okay. This why in the previous chapter we also mentioned there's a bit advantage. Okay, for the multi-collinearity. Yeah. Okay. I think make sure you still remember. Also, we discuss when we discuss the multi-collinearity. We also mentioned, yeah. Multi-collinearity can be a big problem only when the VIF is more than 10. And I also mentioned the problem, the multi-collinearity always there. Just that can be a big what they call. It can be a value, can be a big problem, can be a small problem, can be no problem. Okay, because the meaning of multi-collinearity is that few variables here they have some linear relationship. Multi means 2 or above. Collinearity means a linear relationship. Okay, and for this one, why not good under the multiple linear regression? Because in multiple linear regression, beta I, beta j, beta I, beta j, suppose covariance should be 0. You see, meaning that the sorry, x, yeah. Okay. Covariance between xi and xj should be 0. So they want specifically for the correlation between the independent variables. But now in our context, there are no more independent variable or dependent, or same level. You can see. Therefore, in our context, we no need to meet this assumption. It's okay in our context. Okay.
Yeah, because this is the point of factoring them together, right? They should have a relationship in between.
Yes, correct. You're right. Yeah, because we want to find the common variance, some similar pattern like that. Therefore, they must have some relationship. Okay. Yeah. So therefore, that's why I say if VIF more than 10 is not good. That one is also for the independent variable. But for us, no independent, no dependent. Okay. Therefore, no need to make the assumption. Okay. Okay. So continue. Yeah. Oh yeah. Any other question is? Okay. If no, continue. We are here. Okay. Okay. So this KMO statistics here for each individual variable, and also the sum is a KMO overall statistics. So 2. Yeah. It's quite similar with the T and also the F. T is but under the multiple linear regression, you got 2 T and also F. But now here all on this one statistics KMO. KMO can be for individual variable, can be for the overall statistics. Therefore 2. Okay. So KMO varies from 0 to 1. Yeah. So more than 0.5, consider good. You can proceed with the factor analysis. Less than that is not good. Okay. Yeah. Less than that, what we do, we remove the variable with the lowest individual KMO. Then we test again. Each time only remove one variable. Okay. So until the KMO overall is above 0.5. And then each variable also above 0.5. Okay. Any questions so far? Okay. So
The KMO looks like correlation to me, right?
okay. Yeah, you can consider a correlation. Yeah, but this is they design this for what they call for the factor analysis. Okay. Yeah. Okay. If now we see next one. Yeah, you can say it's quite similar, but of course there must some different. Otherwise, people not going to introduce KMO. They just use correlation. Okay. So we see how to do this using the data. Okay. So analyze dimension reduction factor. Okay. So now we consider everything x5 until 19. Yeah, exercise lah. Okay, exercise. We assume all same. It means same, no independent or dependent. Yeah, all same status. Okay. You put in all the variables here. Yeah. Okay. Any question so far? Okay. Now we see the descriptive. Yes, correct. Okay, descriptive and then anti-image and then KMO. Yeah, both. Okay. So make sure you take these two. Yeah.
Sorry, sir. Can you repeat the step again?
Okay. 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 Now I cancel it. Okay. We see again. Yeah. Okay. So analyze. Okay. Actually variable view also can. Data view also can. Yeah. Analyze. Dimension reduction factor. Okay. So with this, you can move it one by one, but you want to fast, you can use a shift. Yeah, shift and then the arrow down. Okay, you will highlight all the metric variable. And use this button to put in all the variables. Okay. That already highlighted. Okay, if no problem, now we choose descriptive, the first one. Okay, the rest later. We see this one first. Yeah. That means we see before we do data, before we do factor analysis, we should actually make sure that all meet the criteria, okay, of the factor analysis. So we choose anti-image and also KMO. Yeah. Okay.
So what is anti-image?
Okay. This is the term they use, yeah, so that we can get the output. Yeah.
Okay, okay.
So you can see here, actually, it's also one of the correlation metrics. So if no problem, now we see, means the output that we are going to get is also quite similar, okay, with the correlation matrix. Okay, but just use a different method. Okay, okay, so this is the one that we have. Yeah. Okay. Okay. So give you 5-10 seconds, make sure you get the same thing. Yeah. Okay, so now we see the first one is this one. Can you see 0.66? If you use the same data set like from the model, you should get this one 0.666. Therefore, it's good lah. Okay, so this is for the overall data. Yeah, combine all the data, we get this KMO. KMO 36. You can see KMO measure of sampling adequacy. Yeah, MSA. So this is good. Okay. So can you see here anti-image matrix? Okay, it's one kind of matrix. Right. So, if you want to know the meaning, you can check. But we see this only. Yeah. Okay. Okay. So, okay. So the rest we see it later. Yeah. So we see this one first. Okay. So Okay. Okay, now maybe you can see a little bit why they use the term anti-image. So yeah, this got two. Can you see covariance and also correlation? Yeah. Okay. Okay. And then we see also it's okay. Let me skip the anti-image. Okay, we see this you see here got two anti-image covariance and also correlation. We see the correlation. Yeah. Okay. Can you see they stated there the diagonal? Actually, all are the MSA. Okay. Example 0.596 actually is also the MSA for X5. Okay, again, I repeat. You here got two. Okay, the first big table, anti-image matrix, you got two panel. You see the second panel, okay, anti-image correlation. Okay, and this is a matrix, and then we focus on the diagonal. You can see 0.596. This is the MSA for the X5 e-commerce activity. Okay, therefore it's good. This one you should include this. Should include e-commerce because this value is more than 0.5. You can see a superscript A. A is the measure of the sampling adequacy, MSA. You see the note below, at the bottom of this table. Okay. Okay. So if no question, now we see next. Yeah.
So this 0.596 is X5 to its own X5 MSA, right?
This
Was
is only the MSA for X5.
X5.
Yeah.
Okay.
Okay. So actually, therefore, this is also the to see the correlation between this with other variables. Okay, now correlation between this with other variables.
Okay. I mean, in our just now the first correlation metric we saw by right, I mean, if it's a X5 to its own X5 is to be 1. But here is not the 1 because it's I think it's a different calculation, right?
Yeah, correct. Different calculation. This is not the Pearson. The one that we've seen, you will see, you are right, is the diagonal. Okay, you're talking this one, right? You're talking this, right?
Yeah.
Okay, so this is Pearson. Okay, this is Pearson correlation. At least,
okay.
yeah, at least you got three correlation. At least four. Yeah, for Pearson, Kendall, yes, Scaven. Yeah, developed by different people. Okay. Now another one anti-image. Yeah, at least 5. So anti-image is for the vector analysis, different purpose. Okay. Okay. So you see, therefore this 0.596 actually is the correlation between this with other variables. Let's say you remove one variable here, you run again, you will get different value. No more 0.596. Okay, so as what you mentioned just now is correct. They're using different calculation. Okay.
And I saw some MSA is 0.3,
Okay.
0.9, less
Now we
than.
see this now. Okay, we see one by one. Good, thank you. Okay. Now we see 0.596. As long as more than 0.5, consider good. Okay. So 505 914 873. This one not good. Yeah, wait. Yeah, this one not good. 492. Okay. But we record first 492. Yeah, okay. It's below 0.5. Okay. 492 is X9 product line. Okay, 492. Okay. Then we 613, okay. Okay, one more thing, you don't care positive, negative. Negative also good. Okay. Yeah. You can think this way, you take absolute value. Okay. Yeah. So Okay, 512, okay, 309 is the smallest. Okay, 309 is the smallest. 861, okay, 391. This 309 still the smallest. 309, yeah. Okay, 309. So we see two more. Okay, so 309 is the smallest. Any question so far?
So from here, sir, if let's say those number, the MSA is lower than 0.5, we have to drop the variable, right?
Yeah. Okay, yeah, correct, you are right. So, okay, no problem. We see again, whenever MSA is smaller than 0.5, you should drop it and then you run again. Okay. And then each time you only drop one variable. And we should start with the smallest MSA. Yeah, if smallest MSA, meaning that the variable not much relationship with other variables, something like that. Okay. We see we are okay. So we are here. Yeah. So this is the procedure. Can you see 0.5 or higher to proceed with the factor analysis? If it's not, so you remove the variable if the lowest individual KMO. So the value set on the diagonal actually all are the MSA, yeah, for the individual statistics. The one that we seen at the beginning of the output actually is the KMO, the overall. The overall KMO, can you see 0.666? Okay, yeah, this value, the first output. Okay, yeah. Okay, like this. Right, if no problem, now we see where okay. If no problem, now we see the okay, which variable, yeah, is the smallest MSA, yeah, 3.309. Okay, 309, therefore x13, x13, yeah, okay. Okay, so means what? Means if you keep this most probably later we are going to see the new product only one factor. The factor only one variable, something like that. It's not too good. Okay, not too good. Therefore we drop this and then you run again. Okay. So analyze dimension reduction, same procedure like just now. Okay, factor, but now we drop new product. Why not new product? Okay, correct, new product. Okay. So we drop new product, which is X13. Okay. So X13 move back to the left column. Okay. Make sure you still can see the empty image, yeah, and also the KMO. Okay. So yeah, still there. Now we continue and then okay. Okay. If no problem, now we see now a bit. Wait, it's okay. I give you 10 seconds. Okay, no rush. I give you 10 seconds. Yeah, make sure you get the same output like this.
So it seems like not automated one. We have to drop
Yes, correct.
one by one. It's to be automated.
Well, maybe you can do this later because this one is still a little bit new. Not say really new, a bit new compared to the multiple linear regression. Therefore, there are many methods. Okay. Well, example like stepwise. Yeah. Okay. That one already automated. This one don't have. Okay.
Okay.
Okay. So, well, good point. Maybe you can join with other software company, yeah, to make sure that they introduce this feature in the new version. Okay, possible. Yeah.
Yeah.
Okay, we see this. Yeah. So wait. This is O1. Yeah. So the new one is here. Okay. So first thing we see the overall KMO now a bit better. Yeah, just now 666, now 669, a bit better. But we see also the empty image. Okay, the MSA, MSA, yeah, for the individual variable. 0.6 is very good. Okay, 0.6 here is also more than 0.5. 915,869. This was not good. Yeah, 495. Okay, 495. So now 495 is the smallest value. Okay, 510. Okay, now 495. Yeah. Okay. Okay, 394. Yeah, 394. Okay, 394. Yeah. That means we still have two variables. Yeah, with the KMO, the MSA individual statistics smaller than 0.5. Okay. Now we should drop 394. Okay. You should drop 394. 394 is X15 price flexibility. Okay. Now we can do a bit faster. We already run a few times already. We drop price flexibility. Yeah. Okay. Okay. Price flexibility. Okay, remove. So I think based on the previous impact, I think we need to remove 3 variables. They only consider good to proceed. Okay. Anyhow, we follow the output. We do one by one now. Yeah. Okay. So now it's okay. 10 seconds. Yeah. Okay. So now we see the okay. So we see the KMO overall is better than before. Now 0.724. Okay. And then we see the individual also good. 0.59. Oh, here not good. 0.48. Okay. Oh, 0.488. Oh, now got 2. Still got 2. It's okay. But this 2 is quite close to 0.5. Yeah. Okay. Okay. So now got 2. It's still 2. Yeah. So we remove 0.488. Yeah, compared to another one. Sorry, 487. Okay, 487. Okay. Okay. So if no problem, we remove 487. Is it? Okay, correct here. Yeah, we remove technical support. Okay. So we do it now. Yeah. Okay. Okay. So therefore, we remove 3 variables. I put a record because we are going to use this later also. So you can also put a record in your notes. So we next time before we do the factor analysis, we should remove these 3. Yeah. Okay. Put a record in your notes. Okay. S6 and then 613. Yeah, 613 and then X15. Okay. Based on the previous intake, actually only drop three variables. Okay, we see how now. Okay. So 6, 13, 15. Okay, now we run. Okay, still there. And anti-image correlation and also the KMO. Okay. Okay. Okay, as usual, give you 10 seconds. Yeah. Okay. So now we see the wait. Is it a question? Okay, got. Okay. So we see this now. Okay, wait. Okay. Yes, correct. We are removing the variable that with the MSA smaller than 0.5, but this is absolute value. This example, let's say negative 0.7. We want the value. Keep the value. Okay. So, okay. And then we see next. Yeah, correct. Okay, correct. Okay, so where I see first, yeah, remove lowest. Okay, and you run again, correct. Okay, correct. Yeah, thank you. Okay, so correct. Okay, now we see the output. Okay, now it's good. The overall statistics is good, 0.762. Okay, you see, okay, 612 good, 8.8, 0.7, 0.6, yes, 7, 532, 818 also good, yeah. Okay, so 818 and then 751, 814, yeah, so done already. Yeah, this outcome is good, so therefore only drop 3 variables. Okay, so means next time using the same data set, but we don't want this 3, the rest we keep. Okay. Okay, so if no question, yeah. Okay. So we done already for this part. Okay.
So then how about the list of other result below the correlation matrix, the commonalities, they want we
Okay. Yeah, we are going to see this later. Yeah, not today. All is important. Yeah, all these are very important. Yeah. So meaning that
that's
yeah.
why we need to remember.
Yeah, that's why yeah, good point. That's why you need to remember you must drop this 3. Or because we are going to run again. Yeah. Of course, you can also keep this variable. Yeah, okay. But better no need. Just remember the 3 variables that we should drop. Okay. Already good. Yeah, okay. Okay. But it's okay. I tell you some general thing. Yeah, some general. Okay. So example here, we here from altogether 12 variables, we drop 3. Yeah, still got 12. Yeah, 12 left. Okay. So from the 12, we can get only 4 factors. 1, 2, 3, 4. Okay. So component refer to the principal component analysis. Actually, it's also the first factor. Yeah, the first factor, the most important factor. Yeah, the most important factor, they contribute a lot. If this value total 0.4 point something. Okay. So and then you see here got 4 components. 1, 2, 3, 4. Okay. These these values are the factor, we call it factor loading. Okay, factor loading. Okay. Means it's a correlation between between each variable with the factor. These are factors, also called component. Yeah.
Okay,
Okay.
so just now you introduced a few correlation like Pearson correlation. So this loading is referring to which correlation?
Okay, good question. This one is a little bit special. It's not considered any of the above 4 because this one is not the correlation between the variable. It's the variable with the factor. So we did not call it correlation. We call it loading. It's a bit different loading. Okay.
To the factor.
Yeah.
Okay.
The correlation between the e-commerce with this factor. Example, let's say it's high value. Example, complaint resolution 0.815. This variable contribute a lot to the first factor. Like that. Okay.
Okay.
So yeah. You see, this one is good, but not good enough because not easy for us to know the factor 1 should consist of which factor, each variable. Factor 1 should include which variable. Therefore, this one not too good yet. Therefore, we should do rotation later. Okay, rotation should be, I think next class. Oh, no, today. Okay. Okay, if no question, we see next. Yeah. Rotation, at least theory part can be today. Maybe not. It's okay, we see first. Yeah. Okay. If no problem, you see.
Sorry, sir. One question.
ask
Just
now.
now you mentioned that the variance, the chart, the table that's showing that we have 4 factors, right? May I know which
Yeah.
factor consists of which variables?
Yeah.
Are we able to?
From here, not easy to know. Okay. In general, okay. In general, we want the high correlation. Example, X7 should belong to factor 1. X9, suppose X9 should be factor 1 also, because it's quite high. In general, use 0.6 or 0.7. Okay, like that. Okay.
Okay, sir. Thank you.
Okay. So you see more detail later, either today or tomorrow. Either today or tomorrow. Yeah, tomorrow got class. Okay. So continue with the slide. Yeah. Okay. So homogeneity of sample factor solution. Yeah. Okay. So means we try to make sure that each group they have they are all similar. Example, let's say you got two let's say you got two groups, yeah, a male and female. You may make it become two groups. Male, you do one testing. Female is another testing, like that. Okay. Of course, provided that you have enough sample size. Okay. Because if you combine, result maybe not too good, maybe. Okay, this is the meaning of homogeneity of the sample factor solution. Means within the group, they should be quite similar. If they're similar, high correlation. That's the reason. Okay. So, any question on this point?
Just now you talk also on this Q analysis. That one we'll learn later, right?
The part actually not too important. Yeah.
Oh, okay. Just for information.
Yeah. Not too important. Don't worry. Okay.
Okay.
Okay. So, but Q or R not too important, but this is more important. Yeah. So, means let's say your result, your output are not too good. You may also consider using this method. Yeah, means what? The male you do one testing, the female you do one testing. Okay. So because as I mentioned, yeah, within the cluster the correlation may be high. The result may be better. Okay. It's easy for you to find the factors. Okay. Okay. So if no question, now we see next. Okay. So this one is the what you call the pre-testing. Yeah, before the actual factor analysis, you must do this. Okay. Okay. So there must be a strong conceptual foundation here to support the assumption that a structure does exist before the factor analysis is performed. Okay, actually we done already. Okay. No, a bit more. Yeah. Okay, we see this. Yeah. So we see statistical significant Bayesian test of superiority. Okay, a bit difficult to pronounce. Okay. So the p-value must be less than 0.05, indicate that sufficient correlation exists among the variables to proceed. Okay, we see this one now, we still have. Okay. We see the third model, not the fourth model. We drop 3, yeah. Yeah. Okay. So yeah, can you see here? This is the one I mentioned, less than 0.001, therefore it's very good. This we reject the null hypothesis. Okay. Yeah. So therefore, both actually support us. If the data has high correlation, then we can proceed. Okay. So the KMO and also both Bayesian test, both. Okay. So no problem. I can show you the hypothesis. Okay. Now, yeah, it's a simple one. Yeah. Okay. Okay. Yeah. Sufficient correlation. Okay. there's no sufficient correlation between the variables. Okay, so of course this is sufficient. Okay, this is the hypothesis. Okay, for the Bayes test. Okay. Okay. So if no question, now we see no one. Confirm? Okay. So we see next. Yeah. Okay. So MSA actually also discuss. Correct? Yeah, correct. Okay, correct. Okay, for both overall and also the individual. Okay, less than 0.5 should be omitted. Same thing. Okay. Only one at a time. Right? If the smallest one be omitted each time. Okay. Done. Okay, so we see next. Okay, so now we are here. Selecting the factor extraction method, either common variance or component analysis. So, okay. Determining the number of factors you have to represent the data. Okay. So you will see this data. Okay. Actually, of course, we focus more on the factor analysis. Right? So, okay. So for us, still more to the factor data driven. Okay, data driven. Yeah. Okay. So means let the data decide how many factors that we have. Right. So, but actually sometimes we can also, I think we can. Yeah, we suppose can also give some. I mean, give the guideline. We can provide the number of factors here to the software. Okay, I show you now. Yeah. Okay, can I, no, this is the it's correct here. Can you see? Yeah. Okay. So this is Euclid value. You see this in the Showa, either today or tomorrow. So you can also fill in this. Means we have the option. Do you want to do this or not? Okay. Means the extract based on what? Based on what criteria? You can choose one, not two. Either based on Euclid value or you force the software. Yeah. They say, okay, give me 5 factors from 20 variables. You give a fixed value. Okay. So this one is based on the data driven. Okay. So this is standard. Not say standard. Normal common practice. Every value should be more than one. More than one means good. Okay. Yeah. So you see this in the Showa. Yeah. Okay. You see the slide. Okay. So, of course, there's some methodology that we can follow. Yeah. Let's say, which which one you want to use? Either Euclid value or we fix number of factors. Okay. So another method is that we use Euclid value. Some common practice we use Euclid value. More than one consider good. Okay. More than one means they have more higher relationship between high correlation, okay, among the yeah. Okay. More than one, meaning that you have enough variable contributing to the factor. Okay, more than one. Okay. Means high correlation also lah. Okay. Means you can use this method first. Let's say the software give you three factors. Okay. And then what you do, you run again. You fix it 2 factors and then 4 factors. You compare like this. Okay. Means whatever factor the software gives to you, let's say 4, you make it 3 and 5. Before you got 3 tables. Okay. Then you can do some comparison like that. Okay. Yeah. Means you are not totally rely on data. Okay. You can make some comparison later. Okay. If no question, we see next one. Okay. So actually the one that as I mentioned just now, these two actually different not much. Okay. between the principal component analysis and also the common factor analysis. Okay, but still, yeah. Okay. 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 Still, you can see a little bit here. Okay. So the common means common dimension or the common variance. Okay, it's factor analysis. Okay. So component analysis means PCA, yeah, principal component analysis. Okay. Okay. So you see component analysis, what they do, they summarize. Okay. They summarize the variance. Yeah. In a minimum number of the factors, and then for the prediction for the prediction purpose. Okay, so that's the component analysis. Okay, so for common, they find the common dimension or common variance. Okay. So that's the difference, okay, between these two. Okay. So we see okay. Okay, if no question, we see next. Yeah.
Sir, I remember last time I learned something about grouping, which is called K means clustering. Is it something related to that?
I think that one should be cluster analysis.
Cluster analysis is okay.
Chapter next chapter. Yeah, yeah.
Okay. Because when I look, I remember when I learned that last time, it also mentioned something like you need to determine the minimum, so-called factor or grouping for prediction also.
No. Yeah, a bit
Not
different.
really. Oh, different. Okay.
Different. Because in the cluster, we are going to use the categorical variable. Categorical variable is the dependent variable. They here, but here matrix. Okay. Okay. If no problem, we see next. Yeah. Okay. So which method you want to use? Okay. Yeah. So can be this one discussed already just now, but we can see a little bit more what we can do using the common factor analysis. Right? So basically the variance, but they decompose into three what they call three components. Right? So first one is common. Yeah. They say here got four. Yeah. Four variables. Yeah. And they can find some common variance from here. Therefore, they are quite similar. Therefore, they group them into one factor, common variance. So if this percentage, this component high percentage means good lah. Okay, means good. Okay. Another one is specific. Okay, specific variance. So here four. Yeah, let's say four components, four variables, A, B, C, D. So some variance only exists here, not in B. Okay, therefore it's specific. Some variance only appear in the variable B. Therefore it's specific. Okay. So another one is error. Error means something that is some error, maybe due to the sampling error, like that. Okay. Or maybe the respondent did not tell the truth. Yeah, and so on and so forth. So therefore, in general, common variance high is good. They will group together. Okay.
So just to be clear, this variance we are talking is it the same concept as the square of the standard deviation?
No. Oh yeah, correct. Variance is a square. Is the okay. Variance actually is the here is more okay. in this context, you can assume the variance definition is correlation. It's quite similar with correlation. It means these four variables, they correlated together. Actually, the variance is more better. Means it's they're sharing some common feature, common variance. You see? Okay.
Just if we can see example, I mean like SPSS, if we can see what is that common variance.
Okay.
Yeah.
Maybe not now. Yeah, we can, but not now. Yeah.
Okay, can understood. Just to understand this. Thank you.
Okay. Okay, maybe we can give you some numerical example. Manually, yeah. Okay, manually. Okay. Yeah. So I give you two variables. That high. You can say it's correlation. It's also quite similar with correlation. Yeah. Okay. In this context, right? So let's say here got two variables, x3. Yeah. Okay. So this three variables. Yeah. And then x1, the respondent always answer 5, 4. Yeah, 5, 4. Like this. Okay. Yeah. Okay. So you see, this is the same. The respondent 1. Yeah. This respondent 1 answer 5 and 5. Here 4 and 4. 5 and 5. 4 and 5. Yeah. So 5 and 4. That means why the respondent answer x1, x2 quite similar? Because x1 and x2 they are measuring the similar thing. Example, yeah. Let's say always think want to perform better. Always think how to perform better. Okay. Always think how to perform better, yeah, in their work. Okay, work performance. Okay. So and then always try to meet the best. Yeah, to meet all the deadline. Okay. Okay. So therefore, these two things actually lead to commitment. Basically, it's linked to commitment of the employee. Okay. Okay. So therefore, this employee should be high commitment. Therefore, always answer. I mean the employee one 5 and 4, 5 and 5. Yeah. Employee 2, 4 and 4. Meaning that these two looks like they are measuring the same thing, the correct thing, correct dimension. Okay, which is the commitment. Okay. Therefore, they are quite similar. Means they should group together in one factor. And therefore, their common variance also quite high, quite similar. Okay. If we see another, we see another example, x3. X3, okay. This is a different thing. It's different thing. And then this employee 1 answer 3. Here answer 2, 1. Sometimes 5, like that. Means you can see the pattern 2 and 3 should be different thing. They suppose measuring a different thing, they should not group together. Can you see? Because why employee 5 answer 4 and 2, sometimes 5 and 1 for different employee. Because these two are two different things. No common variance, not much correlation. Okay. So
Yeah,
example,
it's quite
example,
correlation.
okay, example always think want to leave office, yeah, before 5. Okay, at 5 quite on time. Yeah, 5:01 example. Okay, example. Okay, example. Okay. So it means even work not finished, yeah, but still go back, yeah, at 5:01. Yeah, like that. Okay. So maybe not too good. I'm not sure. Okay. Maybe different industry, different practice. I don't know. Okay. So maybe other thing, other factor.
What can you
Okay.
finish last
Or
year?
always want to think how to get MC. Yeah, okay, like that. Therefore, of course, not good lah. Okay. Okay, this is an example of the common variance. A and B quite similar. Okay, yeah. But B and C, no. Okay, so if no question, now we see.
Yeah, so here I can understand. I mean, if two data like they go into the same direction, one is up, the other is up, then they can group together. But just it also seems like the correlation, right? I mean, if we use let's say a Pearson coefficient, there's also a good correlation. But variance, just I'm not sure whether there's a mathematical formula for that variance, the common variance that is mentioned. Just to understand the variance only.
Okay. Okay.
Or maybe
Maybe another thing, we don't use variance, but in the textbook there's a term that they use. Okay. So maybe if you want, you can use covariance, because okay, because covariance and variance actually also quite similar. Okay. The formula actually quite similar, but covariance is for two variables, yeah, for x and y. Yeah, covariance for x and y, but variance must be variance for x or variance for the y. Yeah, actually, if you think this way, you may understand better, because they are actually quite similar between variance, covariance, and also correlation. Okay.
Yeah, variance is the standard deviation to the power of 2 lah.
Yeah.
Is that one? Oh, okay. Common variance, that means okay, in the same range. Okay.
Common variance. Okay.
Okay.
Okay. So
Thank you.
we continue. Yeah.
Sorry, sir. One more question. I just
Yeah.
posted a screenshot on the chat there. So if I want to make sure that the variance are similar, I need to make sure that it's more than 0.6 and 0.7, right?
No. This is not
the variance.
This is correlation.
I see. Got it. Thank you, sir.
Correlation. Yeah. Okay. Yeah. But the point that you mentioned is correct. You must make sure that they have the high correlation, high Pearson correlation. So normally it should be more than 0.7 or more than 0.6. Okay. Okay, so if no problem, now we continue with our discussion. Okay. Now we see the rotation that we mentioned also in the yesterday. So we got two. Yeah. Okay. So how to rotate? Yeah. Okay. So remember this one, the last one. Okay, the last one is correct. This one. Okay. This is before rotation. Yeah, before rotation is like this. Yeah, therefore it's very difficult for us, yeah, to find to see which variable belongs to which vector. It's difficult. Okay, so we can do rotation. Okay, so you see the idea. Okay, can be orthogonal or oblique rotation. This one means no relationship. Yeah, no, uncorrelated. Okay, follow the term. Yeah, uncorrelated. Okay, so uncorrelated between x and also the y. Here means this correlated. Okay. So we see the actually here already this. Okay. So we see this also later. Okay, but we see this one. Extraction method determines the type of variance carried into the vector matrix. Right. The diagonal value must be 1. This is the correlation. Okay. The variance, the total variance, you got 2. Yeah, the common, which is the commodity. And then total variance, you got 2 kind. Common, actually 3. Common, specific, and error. Got 3. If the common part is high, it's good it's very good. So therefore the few variables, they're supposed to group together. Okay. Therefore, the variance extracted or is used. You can see it's used. Okay. So, but this one is not used. Okay. So therefore, common variance small means not going to use. Not going to use the variable. Okay. Okay. So okay. Okay, continue. Yeah. Okay. So we see the principal components or common. Yeah. Got two criteria. Depends on the objective. Yeah. So discussed already just now. Yeah, about the objective of the factor analysis at the beginning. Yeah, in the stage 1. Okay. Amount of knowledge, prior knowledge about the variance in the variable. If you know a lot, before you may use the C. Okay. So whether you know a lot or know a little bit about the what do you call about the variance. Okay. So let's say if you have a little knowledge about the okay. Let's say if little knowledge about the specific error variance. Okay. And also the specific variance. Very little. Not much. Okay. Error variance and also the specific. Means what? Means this part. Okay. Okay. So therefore, you may use the factor. Okay. So if little, then you can use factor. If you more, then you can use the principal component analysis. Okay. Okay. So for I think discussed a bit just now. The principal component is for prediction. Okay, it's for prediction, and then this is for the you want to reduce the factor into only few. Into few factors only. Okay. So this is the difference. Okay. If no problem, now we see. But of course, basically we still use these two still different, not too much actually. Because you cannot find the common factor analysis, but you find the principal component analysis in the SPSS. Okay.
So this common factor analysis is the exploratory factor analysis, right?
Again, your question?
I mean, in the beginning, we talked about the exploratory factor analysis and
Yes,
common
common is refer to a factor model, factor analysis,
So this
common,
common, in fact, is the first EFA, right?
no, refer to all the factor analysis.
All the factor analysis. Oh, okay.
But not too important because we only use the principal component. You can see in the HPSS. Okay, even factor, therefore, these two are quite similar. Okay, quite similar.
Okay.
Worry too much about this. Okay, we see next. Okay. So now we see. I think enough time at least for us to get the output. Okay. Discussion maybe tomorrow. So number of factor. Okay, discuss a bit just now. Okay. So the priority criteria is based on the example. Yeah. So based on the journal article, you constructed 20. Let's say 30 lah, 30. 30 variables. And then your sample size also a lot, 2000. Means no problem. Okay. So now based on the journal, you constructed 30 variables. And then you make use of 6 means you're targeting 6 factors. Means 5 each. 5 question, 5 variable for each factor. Therefore, here you just follow your data. You follow your data. Okay. So, but again, sometimes the data come from other people with no control. People ask you to analyze the data. I give you, I point you as the consultant to analyze their data. Yeah, you just analyze. You cannot change anything. Okay. Okay. So next. Yeah. Second method is the eigenvalue. Yeah. Okay. Eigenvalue. Okay. So if the value is high, meaning that if the value is high, meaning that they have high correlation. Yeah, high correlation between the variable with the factor. Okay. Okay, this is eigenvalue. Okay. So we can get the eigenvalue from the I think I can show you. Yeah. Can. We have this. Yeah. So eigenvalue can be more or less. Yeah. So eigenvalue for each factor. In general, we use 0, 1 by 0. Example here. Can you see? Yeah. Okay. So this actually all refer to eigenvalue. 4.8. Can you see the total variance explain the name of the table? You see the component 1, the total dimension 4.836. Yeah. From the output just now, we use the sorry. I'm sorry, we take this one. The number 2 from the bottom. Yeah. Okay. So we take this table, number 2 from the bottom. Okay. The eigenvalue, this is all eigenvalue. Yeah, 4.6791. Okay, eigenvalue. So eigenvalue more than 1, we accept. Smaller than 1, we don't want. Okay. So for factor 1, eigenvalue is quite high. It's 4 point something. More than 1, consider good. Below than 1, don't want. We already set in the default in the SPSS. Okay. Okay. So okay.
So does it mean we need to drop component 5 until 12?
Okay.
I mean the eigenvalue, the column total, if less than 1, we need to remove. Is it?
Yeah. Anything remove below than 1, we don't want.
Because if
Yeah,
we look at the component 5 until 12 is less than 1. So
yeah, correct.
so we need to remove.
Not say remove. We only take the first 4.
Oh, okay. Got it. Thank you, sir.
Okay. Okay. Now we see how they get 39.92. Fine. How? Yeah. They take because here 12. Yeah. 1 until 12. Therefore, the total must be 12. The total eigenvalue must be 12. But component 1, they already take 4.7 something. You use this value 4.791. Okay, I'll show you no problem. Okay, 4.791 divided by 12 times 100. Okay. So this is how you can compute the where is it? Okay. It's correct here. Can you see? This is how you compute 39.925. Okay. Okay, you can try. Yeah. Okay. Like this. Okay. Any question? Yes.
So, sir, this component 1 to 12 is correspondent to the variable just now, the x, the x19, right?
It's correct. Okay.
Then basically the
correct.
first, then this is like not a factoring, but it's like removing the other variables, right?
This is factoring because we get the first. Sorry. This 12. This 12 is not the variable. Yeah.
Oh, it should be a model, right? It's something like model 1 to model 12.
It's not the model, it's the factor. It's
The
a factor.
component is factor one. That means factor one. The component one could be consists of few variables.
Yes, correct. So
But
component one
we
consists of few variables. Yes, correct.
but it didn't show which few variables yet, right?
Yeah, therefore you can see from here, component one, yeah, here.
But
Okay. So this one is the contribution of each variable to the component one. If the value higher, they contribute more. They explain more the factor. Example X7, high chance. This variable should belong to factor one.
so
Okay.
in the end, these four factors, there should be no overlapping, right? I mean, the variables should belong very
No. Some of them they may have some overlapping. Some maybe.
or can
Yeah.
be overlapping.
Yeah. Therefore, for us to make sure that to reduce overlapping, we can use rotation. Okay, rotation will make our life very easy. Okay, you can also see one thing. Component one, the eigenvalue is quite high. Therefore, the factor loading all high value. You compare component one, component four. Component four, the value quite small. In general, can you see?
Okay.
Yeah. So therefore, component 4, the eigenvalue is smaller compared to component 1. Yeah. Component 1, 4 point something.
So
Okay.
it's still not yet finalized that we were going to have four factors only. It could be maybe 3 or 2 later.
Yes, correct.
Later we see the situation.
But if you don't want to change, because it's data driven, the
Yeah,
data gives
okay.
4. This is 4, unless you want to make it 3 or 5, also can. Okay. Let's say you make it 5. Therefore, they consider also eigenvalue 0.732. Also consider become 5 factors like that.
So eventually it's let the rotation to decide how many factors.
Yes. All right. Okay. Of course, we can see rotation later tomorrow. Okay. But now,
okay.
Now we see a bit more eigenvalue. So this is how we can compute this column 39.925 and so on and so forth. Okay. Now we see the cumulative percentage. If consider only the first component, therefore 39 point something, but they say 2 means you take 39.925, you plus 18 point something, become 58.540. Okay, this cumulative percentage. Okay, so now we did not consider everything. If consider all 12 components, will be 100%. But now we only take the first 4. Therefore, 77.704 is the cumulative percentage. You can think of this value is quite similar with the R squared, quite similar. In that these 4 components or 4 factors, they already cover 77.7%. Okay, yeah, like that. Okay, yeah. So the rest because we cannot take everything, we only want the important factors. Okay. Okay. So of course the right side, the 3 columns is the extraction, means it's the extracted sum of square ruling. Yeah. It's the same thing with the first 4 here. Okay, not? It's the same thing. Yeah, but easier for us to read. That's it. Okay, this one. You see, 69.121, 69.121. It's really the same thing. Okay. Okay. Any question? Yes. Okay. So if no, I think the rest will be next class. Okay, next class. So tomorrow, okay. So as usual, tomorrow we start 7:30 until 9:30. Okay, this for tomorrow. Okay.
So just one thing. I keep on thinking on the variables that we remove. So it's totally remove and ignore and forgotten. We're not going to treat them like an error or miscellaneous or anything. Just forget it.
Okay, good question. the variable that you mean the 3 variables that we ignore?
Yes, yes.
Okay. So means, what's the point for you to consider the 3 variables if if the MSA is small, means they are not fit to the data. Means their correlation with the existing the existing variables are quite small. Yeah, you can consider it like the outlier. Then we can ignore, we can delete, something like that. The idea is quite similar. Yeah. Okay.
Just taken out. Okay, okay. Can.
Okay. Yes. Just taken out. Yeah. Yeah. That means not going to use in the data analysis anymore. Yeah. But of course, when you do the methodology, you mentioned that you have let's say you have 30, but in the data analysis final only 25. You must mention why you remove this 5. You see, you must explain a bit in the data analysis part. Okay. Yeah.
Means using MSA below point below is not enough. Have to have some logic behind or no?
The logic part actually not much important because the logic part you already discussed at the very beginning. Correct? Let's say in your capstone, you already discussed, you include this. Yeah. Okay. But of course, let's say for assignment, no need. But for capstone, you may explain a bit more why you remove. Example, maybe data not too good. Maybe the question not too clear. Maybe the respondent don't want to answer this question or whatever. Some sampling error. Yeah.
Okay, okay. Okay.
Okay, so if no question, so see you tomorrow. Yeah, thank you.
Thank you. See you, sir.
Thank you. See you.